Okay, please, thank you.
Uh, about our special format of this meeting. Of course, as mentioned, was mentioned by academician Zagorodny, it's difficult to feel the atmosphere of the meeting. I remember many meetings in the Institute of theoretical physics. It was always very pleasant, but of course, in our situation, it's not so easy. So I hope and I wish to everybody the peaceful sky, and I hope that in the nearest future, after a real great victory of Ukraine, we will have the opportunity to meet directly in the institute. From the other side, it's also not so easy to express in English my emotional state, but nevertheless, Kyiv Institute is very, very important institution for me. I would like just to mention that 8 years I was in the staff of the Institute of Theoretical Physics, working in the Lviv division of statistical physics of this institute, and this experience was very important. Now, about the subject, about the topic of my report, I was thinking on this topic, but in fact, the main reason was very simple why I use such title, Statistical Hydrodynamics of Liquid. I will say a few words on this subject a little bit later. So the outline is very simple. After a short introduction, I would like to recall some basic concept of non-equilibrium statistical operator method. Then I will describe the method developed in our group, method of generalized collective modes. After some application, will be short conclusions. What was motivation? The main motivation was that I recall that for 30 years ago, two prominent physicists went away, and both of them were really great theoreticists. They are Mykola Bogolyubov and Dmitro Zubarev, and both we lost both this person in the same year, in the difference in few months. So it was important for me to show the tradition of the investigation in the field of non-equilibrium statistical physics. I'm sorry.
Продовжуйте, будь ласка, це шум.
And therefore, I choose such subject. So, when we are speaking about non-equilibrium statistical physics, the main contribution in this field, in the area of former Soviet Union, was made by Professor Zubarev, who used several very prominent ideas of Bogolyubov, and the starting point, of course, is the Liouville equation. Standard Liouville equation is reversible, so they introduce the conception of quasi-equilibrium statistical operator. Here is given the form which is closer to hydrodynamical, generalized hydrodynamical description can be used. We can use also another form for the quasi-equilibrium operator, which gives us the possibility to derive several forms of kinetic equation. But for our treatment, we start from such a choice where the P is the operator which describes the density of physical quantities which are slowly changing. When we look on the structure, we see the structure which is very similar to the statistical operator in great canonical ensemble. So P are mainly connected with the density of the concept quantities, and in this set we can also include another slowly changing operators. There is some consistency equation, and in such form the Liouville equation already allows to find the solution which with the some arrow of time, and after hydrodynamic limit, when we use the limit epsilon tends to 0, we will have the term for the non-equilibrium statistical operator, which can be used in our study. The formal solution can be written in the form mentioned here. This formal solution is presented using the so-called Kawasaki-Ganton projection operator, which acts on the statistical operators. And we have also some exponential t-ordered, time-ordered operator, which describes, in fact, the evolution of faster variables. Another form of this formal solution can be given when we use the Mori-like projection operator. In this case, this operator acts already on the dynamical variables, and here we have the ruler which define, in fact, this kind of generalized Mori projection operator. And we have another form of the formal solution of Liouville equation. This form can be used in order to derive the equation of macro dynamics. This means that we have here already the equation for like transport equation for time derivatives of average dynamical quantities with some function which depends from different times. In fact, it's already seen that we have something like generalized transport function. In fact, when we look on this form, it's in fact impossible to use this solution because we obtain very complicated operator with not in this operator we have not only the Liouville operator but also the projection operator, so it's very hard to use in practice such a kind of solution. So we can make the next step and consider the small deviation from equilibrium, and in this case we consider the small deviation from the equilibrium meaning, and this allows us to derive the linearized form of the series, or some of to develop some form of linear response series. The static correlation function are defined in the way you can see here, and in this form we can use all the equation for classical or quantum system. In both cases, it's possible to use such formulas. The deviation from equilibrium, the solution for deviation for statistical non-equilibrium statistical operator in linearized form has simpler form, and now we finally could write down the linearized version of transport equation with rather general structure, where some frequency metrics describe the propagating modes, and dissipation is connected with the contribution of memory functions. But what is important in this context, that it easy to show that equation for the equilibrium time correlation function has a very similar structure as was obtained for transport equation, and what is important that in fact this matrix equation is explicit one. So when we use the definition of frequency matrix and matrix of memory function, it can be easily shown that in fact this is the identity. It's clear from this form that spectra of collective excitation is defined by standard way as a solution of such a question, and in fact we can also obtain the expression for the dynamic susceptibility. So in fact we have the complete basis for next application of the theory in the way that is described in the several books of Professor Zubarev. Some subtotals. We obtain the matrix equation for Laplace transform of time correlation function, and it can be shown that in fact we have the identity, not equation, when we use the correct definition for all the quantities which are in this equation. This main equation forms the basis for description classical as well as quantum systems, and the main problem in application is to find the appropriate expression for memory functions that describe faster processes. So usually the problem is how to find the memory function, and standard way to proceed further is to use some kind of approximation for the all metrics, all elements of matrix of memory function. It's standard way to use the Markovian, Gaussian, or Lorentzian type of approximation. But in this case, we have to remember that using approximation for the memory function, we don't have some systematic way how to improve our result if it is necessary, how to control the approximation. So the main problem is still open. It is connected with the implementation of such kind of theory and with some problems connected with the approximate scheme for calculation of the memory functions metrics. We consider now the first step which allows us to develop the theory. When we, as a starting set of dynamical variables, consider the special set with where A0 denotes the slowest variable in the system, and then we add to this set the time derivatives of this initial set of dynamic variables. So we have some vector with special structure that each next element is just time derivative. In this case, time derivative can be found as action of the Liouville operator. So we have initial set of variables formed in such a special way. We can also construct another set of variables which are just orthogonalized using any kind of procedure which allows to find the orthogonalized set of variables, and for instance Gram-Schmidt procedure, and to form another subset, another set of equivalent set of dynamic variables which can be more convenient for analytical studies. So in this new Y set, the components are orthogonalized, and we have the relation mentioned here. It's possible to do using the projection operator. Projection operators are defined as in the following way, and it's clear that both set of dynamical variables are just connected via some matrix relation.
Ja?
Now we can
Omdat het er zoveel werd gebruikt.
Ja, precies.
On the structure of the frequency matrix, and you see that this matrix has a very nice block structure where only three subdiagonals are non-zero, and in other places we have zero, and all the elements here are defined in this expression, and here we have in the upper level we have the unit matrix. So the generalized transport equation also could be written in such a way Here we see that only one block, the highest order block of the matrix of memory function, is non-zero. The definition of the matrix elements are given here. So we have the transport equation written in the matrix form, and in similar way we can obtain the equation for the Laplace transforms of the time correlation function given below. The problem still exists. We have to find some approximation for the memory functions, but we can consider the Markovian approximation. So this block just has to be approximated by the values at z equals 0. Or used another approximation like it was discussed before, Gauss, Lorentz, and so on. But look on the relation between the memory functions obtained for different sets of dynamic variables. Here we have the block of memory functions, non-zero block of memory function for a reduced set of dynamic variables for when we consider just time derivatives to the order s minus 1 and connection with the memory functions for extended set of dynamic variables. So we see here that when we use the Markovian approximation for highest level, it gives a Lorentzian type of approximation, the explicit structure of Lorentzian type of approximation for lower order memory function. So the Lorentzian approximation just is integrated in our scheme when we change the set of initial dynamical variables. There is also another possibility which was also considered in our study, which follows from this relation, because we can use this relation for the calculation of approximation of memory functions of higher order. There are also another possibility which is connected with the mode coupling theory approach, but it's well known that in many cases such theory is poorly controlled when we are speaking about the accuracy of the result. In fact, we have already some way how to proceed further in the systematic way, because we hope that when we perform the calculation for some fixed order of time derivatives included in the basic set of dynamic variables, then we can compare the obtained results with another calculation which are performed for the extended set of dynamical variables. We hope that in such a way the procedure will be convergent. It's one important point. When we use the Markovian approximation, our problems becomes even more pleasant, because everything can be reduced to the problem of eigenvalues of some generalized hydrodynamic operator. So we have to find the eigenvalues and eigenvector, And the solution for equilibrium time correlation function can be written in very simple form. We have just the mode contribution because this eigenvalue describes the solution for the spectra of collective excitation with some mode coefficient which describes the mode contribution each of mode. Such presentation is very useful, especially when we would have the task to understand the result of real experiments or experiments which are performed using the opportunity of computer simulation. We can also reduce one variable which is very often considered as a fitting parameter. I am talking about the memory function in Markovian approximation because I would like to recall you that this equation, when we use the explicit definition of the frequency matrix and matrix of memory function, is identity. So this property can be used for the calculation of the values of memory function in Markovian approximation. So finally, what is also important, we found the analytical solution for the equilibrium time correlation function. We have the spectrum. We have the generalized question for transfer properties, and the problem becomes very attractive for practical implementation. But even in this case, there are some additional difficulties because to perform the calculation of static correlation function which are needed, to perform such calculation, it's more easily for the initial set of dynamic variables, but it's easy to show that we can, using this matrix transformation, to connect the for instance, to connect the matrix of equilibrium time correlation function defined on the both set of variables, and so it's not so difficult to obtain the result written in different for different set of dynamic variables. What is also very important, when we have such kind of solution, it's easy to prove that, in fact, there are several advantages. The first one is that we can derive that in an analytical form we can perform the so there is some differentiation rules, and there is connection between the time derivatives of equilibrium time correlation function defined on the variables from our set with another time correlation function defined on the same set and connected with order of time derivatives. And such rules are valid for explicit function, and they are also valid for the approximate solutions that we found before. This gives us the answer about the sum rules, because using such rules, it can be proved that some rules obtained for the variables defined on A0 set satisfy 2s plus 1 frequency moments, but also when we use the identity for the which follows from the equation for time equilibrium time correlation function, also to save the zero order time moments for such a function. So we have control also for our result, because when we fix some order of time derivatives, we can control in our analytical firm can control the order of some rules that are exactly performed for our approximate solution. It's really important advantage. So as some conclusion, I would like to recall that we can control the order of approximation, and this control is connected with the control on our sum rules. We found the solution, and which can be written in the form useful for interpretation of data. We have the collective mode of spectra, and we can study the physical mechanism of formation of each mode, and to study in detail the mode contribution. And new possibilities are open for calculation of generalized transport coefficient, because the generalized transport coefficient, when we define the initial set A0 on the density of conserved quantity, give us elements of lowest order memory function. What is also interesting that the theory is formulated in the form which is friendly for connection with computer simulation, and allows us to use some data from computer simulation, for instance, for static correlation function and for hydrodynamic correlation time, in order to find all the quantities which are not so easy, even sometimes impossible to find directly in computer simulation. In order to develop this link, we, together with my colleague Ihor Mryglod and Reinhard Volk, consider this problem in more detail, and propose several algorithms which are much more effective comparing with the existing one. And also mention, I would like to mention that calculate even the higher order frequency moment using standard approach of equilibrium statistical physics is very difficult, because when we consider higher order frequency moment, we have to take into account the higher order the distribution function, for 3 particles, 4 particles, and so on. And starting from some levels, from 4 order frequency moments, in fact, becomes impossible to calculate such moments. But computer simulation allows to avoid this problem because we usually use the molecular dynamics for classical system. It's based on the mechanics of Newton mechanics, and this is the mechanics of the second order derivative. So any order frequency moments can be calculated very easily without any additional assumption, just because specific of Newtonian mechanics. Now about some possibility which were used to apply this formalism. First of all, we use the formalism of non-equilibrium statistical operator to make the link generalized hydrodynamic with non-linear, non-equilibrium thermodynamics. Many attempts were made phenomenologically to construct the generalized transport equation and so on. And here we have the rigorous link how to check both kinds of theories and to find the problems in phenomenological approaches. The second way was theory. It was needed to testify, so we consider the convergence of our results, perform the calculation for time correlation function, spectral, mode contribution, perform the calculation of generalized transport equation, and compare the results with computer simulation for the function which can be calculated directly in computer simulation. We consider several classes of collective excitation which were known, and some of them were a new one, and calculate the collective mode spectra. Also we use this formalism for construction another schemes for calculation of higher order memory function when S is large one, and this allows us to obtain to propose some additional new NZs for the calculation of memory functions. We consider different objects starting from simple fluids and up to multi-component mixtures via magnetic, polar liquids, molten salts, and so on. Just in order to show how it works, I would like to show you the result which shows the link with the non-equilibrium thermodynamic. When we start just from for simple fluid from the classical set of hydrodynamic variables, we can perform all the calculation and find the rigorous relation which gives the definition of, for instance, for dependent from wave vector specific heat at constant volume via correlation function. For all the quantities which were used in the non-equilibrium thermodynamic can be expressed via static correlation function, and this is also useful result for next application. One of the findings is that when we consider within rigorous theory the matrix of memory function, in addition to the standard generalized longitudinal viscosity and generalized thermal conductivity, we found additional coefficient, which in phenomenological theory was not considered because in the limit k tends to 0, this thermodynamic generalized transfer coefficient disappear, but it's play important role when for fixed k and omega. And such terms are not appear in the phenomenological theories because they are 0 in the hydrodynamic limit, and we can show that it's in fact it's a mistake in phenomenological theory. Now about the convergent, I would like just to show one of the first result obtained in our computer simulation in comparison with the theory. We found that already first derivatives gives in most cases very good agreement with molecular dynamics result. When we increase the order of time derivatives, the second order, and so on, we see how in fact the result convergence to the molecular dynamics. Here you can see a very small deviation from data of molecular dynamics. Now a little bit more in order to show how the theory works, I can say a few words about the simplest case of application of the theory, in which we can use the analytical treatment. It's well known the crossover when we consider the spectral transverse spectral function of transverse momentum. We see when k increases, appear additional peak for in the hydrodynamic limits located k in omega equals 0, and then we see the side peak, which usually is considered as appearance of shear waves. Already the simplest model with the first derivative, because you see in the for the description of transverse fluctuation we have only one dynamic variables which are conserved. We already extended this description on one step. We can analytically obtain all the result, and you see that the result for the collective mode spectrum. This result give us two real modes describing just relaxation for k tends to 0. It's written, you can see here, for when k is smaller than some value kh, which gives in fact the propagating gap. For smaller k, we easily can reproduce the well-known results from the hydrodynamic. But for larger k more than ko observable, appear two propagating modes, and we see the appearance of these shear waves. It's easy to check that some rules are performed. It's very simple. And three frequency moments, and also the zero order time moment for the obtained function. So the simplest models already allows us obtain the correct behavior. And we also can calculate the generalized viscosity within the model. It's easy to show that, in fact, such kind of description allows us to derive directly from the starting point, the phenomenological telegraph equation used very often for the description of system with propagating gap. Also, we can use the result obtained for dynamics acceptability and to show, for instance, that in Newton like fluid, we can observe non-Newtonian behavior with relation typical for solids, but for times smaller than some limit value of time connected with T1. There are many other problems which were considered in our treatment. Here you can see some list. I don't have time to go further, but for instance, several points are completely new. For instance, the optic-like excitation in mixtures. They are especially very interesting for salt melts, where they exist up to hydrodynamic limits and can be observed via the relation for partial conductivities and so on. Here I present some list of with review type publication. In fact, we on the concerning the application, it was published about 100 papers, and I would like to using this opportunity to thank them, all the my co-authors, my colleagues on this list. Is very long, but I would like to just name several of them: Mikhailo Tokarczuk, Ihor Mryglod, Andriy Hachkevich, Taras Bryk, Reinhard Folk, Giancarlo Ruocco, Tullio Scopinio, Vyacheslav Koporov, Vasily Natyuk, Wolfgang Fens, Irina Binos, Yuri Rudavsky, Alexander Bacevich, Sergei Dubek. So it's the main part of this list. Finally, I would like to recall that in 1937, to mark the centenary of van der Waals, the Conference of Statistical Physics was held in Amsterdam, and a lot of prominent physicists working in the field of statistical mechanics participated in this conference, and just for joke, or the session chairman Kramers put the issue: with the statistical mechanic can describe the liquid region too often, and the result was 50-50 with the by 9. Voting now, and now we know that thanks Bogolyubov, Zuber, Yukhnovsky, and many others, the correct answer should be yeah. But many problems are still unsolved. Thanks a lot for your kind attention.
Thank you very much. Thank you very much, Professor Mryglod. Very interesting lecture. We are a little bit out of our schedule, but nevertheless, the talk is open for discussion. Please, questions, comments.
May I ask, Anatoly Leopoldovich?
Yes, please.
Ihor Mryglod, as I understood, the letter N means particle number.
And density of particle numbers.
Density of particle number.
Great letter, yes, large letter.
What should I change in your approach if Nx is fixed and what quantities and how will depend on them.
You see, within this, within any kind of non-equilibrium theory, we have always the fixed values which are depend from the statistical ensembles that we consider, but from the other side, it doesn't mean that this value cannot fluctuate within the smaller volume. So we have, for instance, we can consider the ensemble with fixed n, large n, the fixed number of particles, but the density of particles within the local volume can fluctuate. So no, this means what is our task? What we have to answer on what question is?
I ask about fixed n values,
Fixed n, large
not
n.
fluctuated.
The general number of particles is fixed, but
Is large, very large.
but
Well, not
the
very large.
density of particles fluctuates
Not very
Infinite.
large.
in smaller volume.
It is a hydrodynamic approximation.
Okay, more questions, comments?
Question.
Yes, please.
Ігор Миронович, я хотів вас спитати, от на слайді, який називається, in English, okay. The slide with the name Generalized Hydrodynamics, a case of simple fluids. And there are calculated several quantities, heat capacity, for instance, and kappa. And this is averaging of quantities with opposite momentum, hk and h minus k. Does it mean that it is two opposite momentums?
In standard way, the density of particles is defined with the exponential factor ek r sum over r.
Does it mean some kind of pairing? Does it mean some kind of pairing of particles with opposite momentum?
Yes, yes. We because we have here the equilibrium averaging, this means that should perform some law for k and the delta function. We can write down here k1, k2, but it's easily to prove that should be delta function, which gives us.
Okay. So does it mean is it mean that it is stationary pairing or non-stable pairing?
You see here we consider the version of weakly non-equilibrium theory with small deviation from equilibrium. So the in this case we will have here the always law which gives which follows from the conservation law.
And does it mean that the total momentum of the pair is zero?
Yes, yes.
So it means it could be Bose-Einstein condensate of these pairs.
You see,
they can develop.
We can use also, we even try to use such kind of theory to description of weakly quantum Bose-Hayes, but in this case, it's important to it's always important to include into the set of dynamic variables the correct variables which are interesting for us. It's like If we would like to study some phase transition, we always should put into the set of dynamic variables the density of order parameter. If we make the correct choice, it gives us the possibility to correctly describe the general problem.
Okay, thank you. Thank you.
Thank you.
Okay.
Sorry, may be a question. Is it possible to expand such non-equilibrium theory as yours on, for example, to color glass condensate at the first moments after heavy ion collisions? What's your opinion?
This is the first part of my report, which was connected, in fact, in the contribution of Zubarev and inspired by Bogolyubov, gives some general background. And of course, this theory can be used in general case, but in the second part, I was trying to give the way how to proceed further, how we can control the approximation and to have the way to obtain the better control result. And it's also possible to apply it for quantum system. In this case, we will have the more complicated expression for equilibrium time correlation functions. They will be Kubo-like correlators. But it's possible.
Thank you very much. Thank you.
Thank you.
Question.
Okay.
May I, the question?
Yes, please. But
there is some expression for omega as the 3×3 matrix. This matrix have the zero determinant. What does it mean physically?
This means that solution on the eigenvalues will be imaginary. They describe just the frequency of collective excitation without dissipation. When we take into account the second part of the generalized hydrodynamic matrix, it follows from the memory function effect. And in this case, you will have the interplay, you will have the damping coefficients, but without memory functions, the problem can be also solved. And in this case, you will have just propagating mode with imaginary frequency.
Thank you.
You're
okay,
welcome.
dear colleagues, unfortunately, we cannot continue discussions. And I'd like to invite the next speaker, who is Vladimir Sugakov.
We can have a break, maybe.
Probably I'm wrong. Okay.